Hello all, it's Jonathan Kayondo and welcome to Module 3, focusing on pairwise sequence alignment. In this session, we shall learn about the differences between global and local pairwise alignment algorithms. We shall explore the underlying differences or principles behind pairwise alignments, scoring matrices, and gap penalties. And we shall also look at the concepts of the dynamic programming approach for pairwise sequence alignment, both for global and local. Hopefully, from this session, you shall be able to align two sequences using both a global and a local alignment approach. You shall be able to appreciate the effect of various parameters on the quality of the alignments. And you shall be able to interpret the output of a pairwise alignment and also to know when to use the global and when to use the local alignment. Sequence alignment or comparison is a difficult biological task. Shown here are 3 ways that it can be done and the various scenarios to which each is suited for. You can use a dot plot or matrix, and these are useful when you want to have an exploratory view of your sequences in order just to see whether, for example, they are repeats. You're looking for long insertions or deletions and to extract portions that you can use in multiple alignments. You could go the local alignment approach, and here they are more suited for comparison of sequences with partial homology. This ensures that there's high quality subalignments and you have a more detailed residue per residue analysis. You could do the global alignment, and this is comparing sequences over their entire length. Here you're looking for long insertions or deletion, checking of the quality of your data, trying to identify each and every mutation in your sequences, and for making multiple sequence alignments. So how do we go about picking an alignment method? Well, it's not simple, but there are ways to start on that. It's a good practice to start with a dot plot. Dot plots are really very powerful tools that can give you an overview of what's going on. So they can give you possible relationships between your two sequences, and that way they can help you in identifying your next course of action. Dot plots, though, are not enough for detailed examination of your sequences. For example, they're not going to really produce you an alignment in the true sense whereby you get the residue to residue matches. But they are a good start and they're easy to make. If you really need an in-depth pairwise alignment, then you can proceed after dot plot to either the global or the local alignment. For actual alignments, I said there are 2 approaches that could be pursued. Either the global alignment, this is where the sequences are aligned along their entire length, or the local alignment, where only the most similar portions of the 2 sequences are matched. You choose the global way if your sequences are related along their entire length. Sequences don't contain long insertions or deletions. And like I earlier said, a dot plot can show you those relationships very well. So how do we make a dot plot? Like I said, it's pretty simple. The approach here is to generally move across the rows in a grid systematically, placing dots in every column where the 2 nucleotides or amino acids of your 2 sequences match. When you do this, you are going to have patterns emerge, and you are going to draw lines where you have series of sequential dots, and that's how you come up with the patterns in the dot plot. So any region of similarity is going to be revealed by a diagonal row of dots. Isolated dots on the diagonal represent random matches. There are many programs that can help you make a dot plot or matrix, and they make them or they produce them variably. If using a computer programs, they're going to have some default outputs, but remember that those might need to be refined by adjusting various settings. For example, you may need to slide the window size so that you have more flexibility in the range of residues in the vicinity of the matches that you're looking for. So a few tips on the dot plot is that long windows make clean dot plots and they are more stringent. Shorter windows are more sensitive but they come with noise. But they can help in scenarios of distantly related proteins though. The trick is to start large, then progressively reduce until the signal in the question that you're looking for appears, or you ensure that it's really not there. Also, remember that it's good to strike a balance. Being too stringent is as bad as not being stringent at all. So when you're doing these variations in the settings, remember that you have to strike the correct balance. Okay. Shown here is an output from a sample dot plot. See how the two sequences are aligned, one on top, one on the left going down, and you score the matches in the rows systematically until all the scorings are done, and then you draw lines between your sequential dots, and this will be the diagonals in question. So it's very simple. The patterns where you have matches or similarities or repeats will be brought out by the various diagonals. So sequence alignment algorithm. So what's an algorithm? An algorithm is a sequence of actions that are performed in order to solve a problem. And for sequence alignment, there are really two approaches. Either you do the rigorous algorithms that are guaranteed to give you the optimal alignments, or you do heuristic algorithms. So these are faster, but only just approximate alignments. So these ideas were developed in the 70s and 80s, where Needham and Wunsch used the global alignment to solve a sequence alignment problem that was based on a dynamic programming approach. And then Smith-Waterman developed the local alignment algorithm, also derived from this dynamic programming in 1991. And the four heuristic algorithms, these are faster, they came a little bit later, and they're only approximate. And we shall see in session 3 as an example when they come in really very handy. So what is dynamic programming? Well, the basic idea, at least in the case of sequence alignment, is that the sequences to be aligned can be so long such that comparisons of the residues pairwise, one at a time, all at the same time, can be not achievable. Yeah. So therefore, you need a way of rescuing this situation. Also remember that when you are going also to involve the inclusion of gaps to improve your alignment, the number of comparisons are made even higher. So this is where dynamic programming comes in. So for this, the idea is it somehow finds a way of keeping the comparisons manageable by carrying out the operation in a stepwise manner. Okay, just to recap, the dynamic programming ideas for the pairwise sequence alignment, here they are designed to solve for you and get a solution that returns the optimal alignment that can be achieved between your two sequences. But remember that it could be optimal or the highest scoring, but does not mean it's necessarily the most biologically meaningful. You always have to keep that in mind. Also, at the same time, the approach works in a way that it keeps the comparisons manageable by doing or carrying out the problem in a stepwise manner. And this is how it does. So it breaks it up into smaller sub-problems. It solves the smaller problems optimally, and then it uses the sub-problem solutions to construct an optimal solution for the entire problem. That's the gist of the dynamic programming for sequence alignment. So how does it go about the business? Well, the approach is computational, and it considers all the possible pairing of characters between your two sequences. Remember I said it doesn't do that all at once. It breaks it down into sub-problems, and then it scores or finds the optimal ones among those sub-problems, and then it strings them together back so that you get the entire optimal solution between your entire array of your sequences. Now, the highest set of scores, sequential scores in your matrix, we shall discuss how this comes about, defines your optimal alignment. What you have to remember is that this dynamic programming approach really is very computationally intensive and requires lots of computing power. So why is this method or algorithm important? It is because it provides alignment that of the highest quality, as evidenced by the highest scoring, because that's what it returns. So those are your optimal ones. And also, there are lots of programs out there, including web-based ones, that help you with this. You just have to go to the websites and start working, start generating your alignment from them. Remember, even if that's the case, the method requires careful consideration for your choice of variable settings in the program. Their defaults are right, but you should be able to understand what each field really means and what's the impact of changing a variable in that category. Also, the method is highly computationally demanding, like we saw earlier. So what's the procedure for the dynamic programming algorithm? It briefly runs like this. You need to initialize a matrix to guide your alignment path. That will be based on the scores that it generates according to the matches or mismatches that it finds. So this is a computational problem that requires a scoring system. The scoring system itself is derived from probabilities of aligning a pair of the amino acids or matches, so that the probability that they can be aligned in alignments of related proteins is divided by the probability that they can be aligned by chance in the proteins of unrelated, obviously, proteins, after factoring in the relative abundance of the amino acids in questions. So that's how you get the score, basically, of the matches that you get. And sometimes you don't really have to align or mismatch, so you just have to create a gap if that would increase your score in the long term, and the program has a way of finding that. Now, the scores for the alignment of the ratios that you see above, I'd say their probability, but in the tables where you check them up, they're going to appear as substitution matrix compilations. Some of them are palms, others are blossoms, and there are many subclasses to pick from, as we shall learn later. But all of those are going to be the ratios of the two relationships that I described earlier, and we shall learn more about those in the coming slides. Like I said, the scores for the quality comes from a matrix table, which gives you the ratios of observing the frequencies of substitution between each possible amino acid pair, as was found in related proteins, to that expected by chance, as was indicated by the pairings in, say, unrelated proteins. Of course, after adjusting for the relative frequencies of the amino acids in the proteins in question. The scores above are usually odd scores, but usually in the substitution matrix tables, they appear as log odds, just to enable the handling of the calculations to be more simpler. So this is a little bit more example on the scoring system. So we said you use a log odds matrix in the substitution matrix table, where in that table, as we shall see later, you'll see the probability of aligning the two residues that are being compared. Of course, the score of the alignment for the entire sequence will be the sum of your log odds scores for the residues that are involved. For the score of each residue, remember it was an odd score, you have to convert it into a log odd score using this formula. Just use base 2 and then divide the probabilities like we've talked about earlier, and you'll get your log odds scores. And of course, this conversion, like I said earlier, is made so that you can handle the math much more easily, because if you want to multiply the probabilities there, you really if you want to consider, subsequent probabilities that have to be conditional, then you have to multiply them. But if you're using logs, then you can add them. That's the same calculation, and it makes it much easier to just add up the log odd scores and see the actual sum of your to get this actual score for your alignment.